itself, and transforming. We're going to ask you to take something that you're accustomed to, called a parent graph. And I think I gave you a page of parent graphs, basic graphs. And do something with them, shift them around, flick them around, do something with stretch them, so forth and so on. They're called transformations. Now, notice on your handout, someone's going to have to help me out here. You guys have the handout. Anyone tell me what the first transformation was identified as on that handout? Vertical shift. Okay, hang on just 1 second. Vertical shift. Now I'll come back to that. Number two, what was number two? I mentioned another type of transformation and labeled as number two. Horizontal? Horizontal shift. Number three, another type of transformation mentioned on the handout. Reflection. Reflection. Okay, number four, what else was mentioned? Or was there anything else mentioned?
Horizontal stretching and shrinking.
There you go. Horizontal stretching, not shifting. We just abbreviate here. Horizontal stretching. And I heard also what else besides stretch?
Shrinking.
Shrinking. And that's the tough one sometimes to deal with. Was there anything else on that particular handout? I think those are the basics. I hope. Okay. Guys, going back to vertical shift, we should realize when the vertically shift the graph up, when you vertically shift the graph down, that's no problem. That will be no problem. Someone quickly tell me, if the standard form is f of x plus c, and you have to plus some constant on the end, what must that constant be in order to shift down? Just common sense, negative. What should that constant be to shift up? Positive. Okay, that's all we're looking for. We'll try some examples here. Horizontal shift, a little tricky at times. All right, like this. If I write it like this, and I see it listed as this, and x subtracts c. Now the c's inside, not on the outside like the vertical shift. What would that x subtract c may indicate for you to do on a graph? And I have it under the category of horizontal shift. So it's going to be shifted in which direction? To the right. Just a quick review here. If it looks like this, there's an x plus c. Again, it's going to be a horizontal shift, but this time what? To the left. So many units. Reflection. I can reflect across the x-axis, y-axis. So guys, I think we'll do first the x-axis. And let's write this as y is equal to, get that to be done, a negative sign out front of my function. If I want to reflect through the y-axis, and do a good job with it, it will be expressed as this. Now I'm going to be very careful with all this tonight. The negative sign's inside. That will have me to reflect through the y-axis. Now the last one. That one can be tougher. I hope on the handout, did I mention anything here like y is equal to, probably, see if I'm correct, f of maybe cx? Get it right like that? And then whatever that c is, determines whether it's going to be a horizontal stretch, a horizontal shrink. Guys, someone remind me what you know. What about this c value if the c is positive? Suppose inside there, we'll try an example here shortly. You find c is positive, does it, on the handout, does that tell you what should happen for a transformation? Should be a horizontal stretch, not vertical. Is it a horizontal stretch on the handout?
It's underneath horizontal stretching, shrinking.
Yeah, so if it looks like this, f of cx, did I write it as f of cx? Or y is equal to f of cx, is that written on the handout? With the constants inside, because you guys, I haven't used examples yet.
C is 1.
What's that now?
C is greater than 1.
Oh, 1 here. They put 1 there. 1. If c is greater greater than one, what type of a, stretch or shrink should happen here? Does it say stretch or shrink? Stretch, or stretch? Shrink. And of all things, by a factor of what? This is the toughest one, guys, of all the transformations. Was it 1/c? Hit them correct. Yes, no? And if it looks like this, if c is probably less than 1, is that the other one? C is less than 1? What does it say is going to happen? You're going to shrink the graph again, or you're going to stretch it? Stretch it. And you're going to do that by a factor of, here we go, guys. 1/c. Now, those are the basic transformations I'm supposed to do to get the effect, to get a final graph. Guys, let's go back where I tried this with a graph. Can anyone tell me if I'm supposed to take my function and add c, or there's a plus c on the end, and you have some points plotted to work with on the grid, what might you do with your points to make them move up or down c units? We actually have a series or a list of points that belongs to that function, like ordered pairs. What would you do to go through? You're going to go through all those ordered pairs and transform them by doing what to them if you want to get this to happen. You want them to shift up, let's say. What do you think you would have to do to those ordered pairs? Jonathan, go for it.
Each y value add whatever c is.
You go to the y value and add whatever that constant is. So each one of those ordered pairs listed, you go to the y value, and he says add whatever that constant is, professor, and that will shift it up. If I want to shift it down, you're going to go to the y value and do what? Subtract that c value. That's all we're doing. This one, be careful, if I want this effect to take place, that horizontal shift to the right or to the left, and you've got ordered pairs listed. You don't have a graph, you've got ordered pairs. What are you going to do to those ordered pairs, do you think, to make, let's say, the graph shift to the right horizontally? And you got the ordered pairs listed. And you want them, when you plot them, to be shifted to the right of where they originally were. What do you would think you would have to do to the ordered pairs? Anyway, yes? Okay, you're going to do a constant. Okay, hang on now. And you're going to tell me how to do what now? You're going to subtract from the x. Or you're going to add. Beautiful. Beautiful. Hang on to that thought. That's why I brought this in. Okay, let's do it right now. Let's go to a graph. Let's see what on earth, Ramsey, what are you talking about here? I sort of follow what you're doing here. Let's go to a graph and really see what's going on here. Okay, guys, we'll try this. Here goes. I brought one in. Let me see if I have it handy here. I do. Guys, bear with me. I'm going to have a graph that looks like this. Let me take some questions here. I have these points plotted, so bear with me. You have a handout later on with one on there. Practice with. We'll say on this grid, I have a point out here at -4, -2. I have another one here at 0, 2. I have another one at out 2, up 2. I should label these as I go along. And I threw in one more, 4, 0. Not too bad. 1, 2, 3, 4 ordered pairs. I'm going to connect them and get a graph that looks something like this. step back. Guys, it looks something like that. I got all the ordered pairs listed. Now, I would like to find, make it beautiful. First, we're doing it in blue here. Let's name this as a function of, go back to the black. This represents a function, y is equal to f of x. It would pass the vertical line test. So that's the shape of a function, okay? Now I'd like to show on that, I'd like to transform that graph. And I'd like to transform it first by considering this. I'm doing it in blue, f of, here goes. And my first one looks like this. A 2 out front times my function. Now, do we have a transformation listed maybe on your handout that may tell me something may happen here on this one, or not? Or did I leave that out on purpose? Does anyone think they know what the 2 stuck out front might tell me to do to those ordered pairs to get the effect I want? And first, what's the effect? Guys, I don't think this one's listed on your handout. Please tell me, is it doing this? Is it shifting up? No. That would be a +2 on the end. It's not a vertical shift involved. Is it one of these where the C is inside, like an x minus 2? No. Here, no. No, no. I don't have one listed on that handout. That's why I left it out. I want to get the response from you guys. What do you think would happen if a constant is merely stuck out front of the function, and you want to do what the transformations involved here? What type of transformations first do you think would take place? 80, what is it?
All the y values get multiplied by 2.
That's what it says, multiply all the y values by 2. 2 times f of x. Multiply all the y values by 2. I can do that in blue quickly. I start here, multiply my y value, which is -2, becomes -4. That means it's going to make this work for me. I'm on the top of the board here, guys, so watch carefully. Will this point now be down here at out -4, down 4? Yes or no? He tells me 80. I have another point here, 0, 2. If I do the same thing, multiply the y coordinate by 2 as you suggested, that now becomes where? It moves to what?
0, 4.
Absolutely, so I'm just going to plot that. He says, Professor, it's up here. No problem. I have 2, 2. The y coordinate is 2. Multiply that 2 by 2, as he tells me to do. Multiply the y by 2. It now becomes what? 2, 4. It's up here. I'm going to label this. Keep track of it. And the last one was 4, 0. Where the y coordinate is what? 0? Draw on the x-axis, multiply that by 2, stays right where it is. Now, if I'm patient, let's see if I can. I didn't bring my straight edge in I'm accustomed to. Let's see if this will work. Line these up in the blue, and I get something like this happening. I think you guys would agree with that. Guys, does it look something like that when I connect? Now, what type of a transformation took place? Look at the parent graph. My parent graph is that black graph. Then all of a sudden I did what Aiden suggested with that 2 out front, stretched it. Now, what would you say then that transformation should be identified as?
Vertical stretch.
It's a vertical stretch, not vertical shift. Okay, so if the constant stuck out front, it's going to be a vertical stretch. And that's exactly what happened. It's that black graph has been stretched. Number 2, we'll try this one in red. It's way too crowded. So you gotta do this. Have a negative sign out front of my function. Plot this in red. This red will hold up. Now, tell me what you might want to do with those ordered pairs listed to get that effect. Got a negative stuck out front. What do you think a negative stuck out front means to do on those ordered pairs? Yes?
Reflect them over the x-axis.
Hey, I mean the ordered pairs themselves. Those 1, 2, 3, 4 ordered pairs on my parent graph. I'm gonna go back to the black graph.
So reflect the y values.
Okay, tell me again.
Reflect the y values.
Yeah, well, multiply the y value.
By -1.
Yeah, by -1. So if I do, my first point was -4, -2 on the parent graph. If I multiply that y coordinate what, by a negative, that becomes what, -4 up to. So I am now, on top of the graph here, -4 up to, am I right here? My next point on the black graph was 0, 2. If I multiply the y coordinate by, I think I heard what, negative? And now it's where? Is it 0, -2, guys? I'm right on top of 4 here. My next point was what? 2, what was that? Out 2, up 2, out 2, up 2. Now it becomes what? Is it out 2, down 2? Is it true? And if I multiply, finally, I guess I'm out to this, where am I? If I use this point, oh, out here. 4, 0, what about it? It's gonna stay right where it is? Does that make sense? Now, did I pick up all my points, or not? Did I pick up all the points up I need, or not? So when I connect them, let me just connect these for you here. Am I gonna get a piece like this, a piece like this, and a piece like this? Yes or no? Is that the original black graph, you think, what, reflected across the what? X-axis. And I got the effect by multiplying all the y's by a negative to get that effect. That's what's going on in these transformations. Okay, I'm gonna do one more here with you. Let's try, see if I have a marker here that may work for me. Okay, let's try number 3 here. And I hope you can see this, let me know. Y is equal to, we'll try this one. Yep. F of, bear with me, last one we'll do on the screen more likely. X subtract 2. And I think that might fall into the category here. And it looks like the way it's written, it might tell me it's gonna be a horizontal shift to the what? Right, 2 units. Now we'll go back, guys, to my original black graph. That's my parent graph. Consider that to be my parent graph. So on these 1, 2, 3, 4 ordered pairs back on the black, what should I do to them to get that effect? And that's the one we were just discussing, that's why I brought this in. Yes?
Shift right.
And we're gonna shift right, but I'm saying, what are you gonna do to each one of those ordered pairs to make sure your black graph, when I finish, has been shifted to the right? What are you gonna do here to this ordered pair, this one, this one, this one? You must do something to those 4 ordered pairs. When I do it, connect them, my graph should be shifted to the right of the black graph. What are you going to do to get that shift? Yes?
Y plus 2.
So again,
Y plus 2.
he says add 2. I think I heard before, maybe it's subtract 2. Now, is it okay, subtract 2 or an add 2 to get that thing to shift to the right? Yeah, it looks like, some students will like to see that subtraction sign there, they'll say, oh, Professor, it's subtract something, subtract 2. Is it really just the opposite of this one? To make a shift to the right. I've got to be very, very, very careful with that one. Guys, let's do that, this will shift my black graph to the right. Let's start here. I got -4 and -2. I'm adding 2 to the x. Is that true? Is that what it said? I just heard someone say just add 2 to the x. If I do, that becomes negative what? -2, -2. Replotted. Now -2 down to, guys, looks like because my graph is getting crowded here. Is it in here somewhere? Yes or no? Just quickly, I just plotted it in there somewhere. My next point on my parent graph was 0, 2. The student told me it says add 2 to the x. Well, the x is 0. If I add 2 to it, where am I now? 2, 2. So out 2, up 2. And guys, looks like that's going to take me right to there where I was on the other graph. Is that true, guys? So far, so good? My other point now is 2, 2. It's on the black graph. That's got to be shifted also. So if I shift it over 2, it's down where? Is it 4, 2? Is it here? Help me out. me on that black graph was 4, 0, I think. Got shifted over 2 to the right by adding 2. Now where am I? 6, 2. Let's just this marker will hold it up for me here, guys. So let's go out to 6 and show this point. Again, I got those by adding 2 to the x coordinate of my parent graph. Guys, if I connect, please tell me, I'm just free-handed here. It's like one piece is gonna look like that. Another piece is gonna look like that. Another piece is gonna look like that. The grid's getting crowded. Can you guys still see the black graph? That's the parent. The orange one, this color here I just finished up, does it look like the orange one is to the right of the black one? When I compare the black parent graph and the orange one I just did, does it look like it's out to the right of the black one? So it was to add 2 to make that happen. Guys, those are the types of transformations that should happen. Now, we're going to make it much, much easier for you, but hang on. Do I have something here? I do. Hang on, hang on. I thought would be beautiful to bring in. I had better brought it in. Oh, I did. Here it goes. I'm going to give you a point. Everybody help me. This one's finished. I'm going to give you this. This is a point on a graph. I will not graph it. On the graph of a function. This is cute. Okay, no graph this time. Don't worry about this. That point is on that graph, that point is on the graph of f of x. Now, number 1, or find, number 1, this. What point is on the graph of this? Get rid of that letter A here. Y is equal to f of x plus 1 subtract 3. Now this is where it really gets cute. No graph. So I gave you a point that's on a graph and the graph's missing. But they gave you a point at least on there. They're saying if you go through all the transformations, where will this point land? After all, in fact, there's only 2 transformations here on this one. After these 2 transformations are done, where will this point land? And I need not see the graph. Now, I'm going to set it up for you and get some input. Here's the original point. I'm going to do it like this, guys. I'm going to first do the horizontal shift to the left. X plus 1 means what? A horizontal shift to the left, what? 1 space? Anyone tell me what would I do to that point to make that happen? And there's no graph here. What should I do to this point here to make it shift to the left?
Subtract 1.
Subtract 1 from which coordinate? The x. Now the 2, negative, so right now negative 3. So you now tell me it becomes a negative 4. And the y stays the same. That's done. Now it says don't stop there. Now vertically shift it down 3. What does that state do to that point there to make it vertically shift down 3? Subtract from the y. So the y is 5 right now, subtract 3. And I guess you're going to end up with what, 2? And there's my final destination after you go through those transformations. No graph required. Just follow the point here. Next one looks like this. Let's get this done here today. Next point is, yes, find where this point will land if I do this to it. Negative 3 f of x subtract 4 plus 3. I have just one more to do. Okay, so guys, I'm gonna start you out on the side here. Again, same point. And we'll go through the transformations. Now, can someone help me count how many transformations are there to be done on this to begin with? Let's count. The negative sign. What's the negative sign indication should be happening from way back here, somewhere, right here? What's that negative sign say should be happening here? That's when we were reflection across the what? X-axis. I don't have the graph over, that's what should be happening. Next, I see a 3 stretched, 3 out front. What might that 3 tell me to do later? Vertical stretch by a factor of 3. As if that's not enough, this says don't stop there, now horizontally shifted to the right, 4. As if that's not enough, vertically shifted up 3. Now, so after all those transformations are done, where will this point, right here, this point right here, negative 3, 5, it's going to do, where is it going to land? That's what I want to know. Where is it going to land? Now, if you take each one of these transformations separately and do it, I guess, as we should, not try to combine things here. Guys, first, let's get this out of the way. The reflection across the x-axis. Anyone tell me what that means to do on my point here? What should I do to my point to have the effect of it should be reflected across the x-axis? All I see is a negative sign stuck out front. Yes?
Subtract the y by.
No, not subtract.
Oh.
Not subtract, that's what I wrote.
Multiply.
Yeah, you're gonna multiply. Multiply what? By negative 1 or negative 3. Let's say negative first, just negative. Change which one? The x and the y. The y? Okay, now this becomes this then. Leave the negative 3, multiply the y by negative, I got more erase. That takes care of that. Now, if we're going further, in your mind, if you go out negative 3 up 5 on a grid, on a sheet of graphic paper, just visualize, out negative 3 up 5, I think out negative 3 up 5, you're in quadrant 2 on a sheet of graphic paper. You're above. If you plot this one, negative 3 down 5, where are you? I think you're in quadrant 3, you're below. So did that sure enough have the effect I wanted? I wanted it to be reflected across the x-axis, and it is. Now the 3. Someone said a vertical stretch by 3. What should I do here now to make this vertical stretch by 3? Yes?
Multiply it 3 times negative 5.
Absolutely. Multiply that y coordinate by 3.
Yeah,
You're going to end up with negative 15. No problem. We erase this, it's gone. We did it. Next says don't stop there, horizontally shift now 4 to the right. I guess 4 to the right, says x subtract 4. And what should I do here to make that effect, or have that effect? At this point, what should I do? Add 4. And by the way, guys, right now the x is what? Negative 3. If I add 4, you're going to end up with 1, negative 15. We erase. That's done. The only transformation left is 3, plus 3, which is like what? A vertical shift? And to get that effect, what should I do here to finally finish up? Add 3 to that y coordinate, negative 15, negative 15 plus 3 gets me what? Negative 12? Look where we started. We started here. If we've done this correctly, we're guaranteed by the time you go through all these transformations, that point's going to now land here. Out 1 down 12. You guys agree? Now the last one, here we go. And I'm finished with this, except for one little item here. Next one looks like this. Y is equal to f of, I thought I'd bring this in. That. And I'd like to know where will that point land? That's my last I do transformations. Now, somewhere in this clever class, if I have 9 or 10 A's on the first exam, which on the first exam, guys, in most places unheard of. Instructors are lucky to get 2 A's, or 1 A, sometimes none. I've heard some instructors, they get none. I had 9 or 10, so we're doing it. Now, can anyone tell me, what about this last one here, what should I be careful with? What should I do? I want to see some hands going up. Aiden,
Think you should factor out the 3 from the whole thing
I
as
think you're right.
horizontal.
Hang on now. Aiden, are you telling me inside here?
Yeah.
Take out 3. This is cute. This is cute. Now, I've done that. He suggested that. Now, Aiden, since you suggested that, can you tell the class, before we jump into the work here, what type of a transformation where that 3 stuck inside, not out front? I think it was stuck out front down here on this one. It's stuck inside. Is that more of, and then Aiden will help me here, is that more of, I'm looking here, something like this?
Yes,
Happening.
it's a horizontal stretch.
Okay, and the C in this case is what? 3?
Yeah.
And I think the restriction was if that C is what here, greater than 1? Mine's 3, this should what, shrink the graph? If I actually were graphing, by a factor of 1 over C. That's the strangest one of all the transformations. 1 over C, where'd they get that, professor? That's the rule they follow. Aiden, can you tell the class what you might do with this ordered, one single ordered pair to get the effect of, this is going to be a horizontal shrink by a factor of all things, 1/3.
Negative 3 divided by 3.
There again.
Negative 3 divided by 3.
Getting close. I got -3/5. What are you going to do to either -3, the x-coordinate, or 5, the y-coordinate, to get that effect, which should be, I guess, shrink? It's supposed to be a factor of 1 over c, and c in my case is 3, so I need a 1/3 in my case. So which of those 2 coordinates should I deal with 1/3, you think, to get a horizontal something going on? The x or the y? You think I'll get the x? If I go to the x coordinate right now, guys, and multiply it by what factor? 1/3. This will change that into what then? Guys, what is 1/3 of -3? Then -1, -5. I just took 1/3 of it, the x coordinate. And then don't stop there, to finish it up, the way he has presented this to me. He says, Professor, you still have x plus 3 to worry about, which I think is what, a horizontal shift to the left. What might you do in the red there to finish that up, to see that horizontal shift to the left?
Subtract 9 from the y.
Do we get,
Subtract 9 from the y.
a 9, where do you see a 9?
Against
Is that true, guys? X plus 3, does that indicate you're going to have a horizontal shift to the left? 3? It does, doesn't it? Now, what should you do to finally finish this up? What should you do to the x coordinate or the y coordinate in the red? Are you going to do it to the x coordinate? And by the way, to get a horizontal shift to the left, are you going to subtract 3? Are you going to do it from the x coordinate or the y coordinate? X coordinate. So I got -1 right now. If I subtract 3, does that become what? -4? And leave the 5. Wow. Let me see if I had all those written down. Yes. Does that make sense? No graph. I had no graph there. I said pay attention to my transformations. Now you say, Professor, if you give me one of these on the exam, when we finally have an exam, and you give me one little single point, and you have some drawn out transformation like that, and I gotta do this to it, that to it, this to it, that to it, subtract 3, divide or take 1/2 of something, and do this and do it. Yes, you're supposed to now see where this original point lands. This point will land here. on whatever that graph looks like. There's no graph there for me to worry about. That's where I leave it. Are we okay? Now, what we want to do though, close this down on transformation. This is what we want. Hang on, starting something cute here. I did. Here we go. Sketch. Letter D. Now I'm closing this down. As I have written as this, y is equal to this. And I should say sketch using transformations. You guys may want to write that in, using transformations to get the sketch. No point listed here, like on the last set. So what do I need? First, I need a parent graph. And then we'll perform those transformations on that parent graph. Now, by the way, I noticed this one says the square root, and I hope we all recall what a square root graph looks like. That's one of the principal parent graphs. On the side here. And we have this. Guys, I'm gonna place my parent graph in blue. And label it as this. This is what a square root graph looks like. Now, can someone tell me what does this mean to do here? We're not gonna make it too involved. The negative sign stuck out front says what should be happening. Where on earth was it? Oh, right here. So what type of a transformation is taking place at the very beginning? It's gonna be a reflection across the what? X-axis. Now we're to a point now. I don't want you to plot points, just do it. You guys will do this in red. I just want you to do this. And show me. You're done. That's a reflection of that blue graph, parent graph, across the x-axis. It's finished. Then, we're not stopping there. Now I've got x plus 9 to worry about. I think in terms of a transformation that might fit this. Which says I should do what to get the next part? Horizontal shift to the what? Left is the left here? What, 9 units? Okay, so let's mark 9 here. Hang on, guys. Stretch this out somewhat. Here. I calculated that's out -9. And please tell me, here goes, that red graph now is being shifted over there. Does it now, let me put it in this color. I can. Does it now look like this? The red graph shifted over 9 units to the left. Don't stop there. Now take that orange graph, don't stop there, and do what to it? That +4 indicates what? Where am I? A vertical shift up 4. Which merely says to get the last graph here, we'll try it first. You're supposed to shift up 4. Here. And you say, Professor, you're supposed to shift what up 4? This. This was the last graph, I think, wasn't it? And I'm supposed to shift it up what? Vertically shift it up 4. If I do, please tell me, will the last graph look something like this? Shift it up 4, I guess I'm right there. And will it take a shape something like that? Yeah. Is that true? And that's my last graph. That's seeking. We did through transformations. Now, I do see the endpoint up here. I think the endpoint is -9 up 4. Now, what am I gonna do here to close this down? Beautiful. With my green graph, which is my answer, with my green graph have an x-intercept? Does it cross the x-axis somewhere?
Yeah.
And if it stretches further, does it cross the y-axis? So I always ask my class to finish up, refine it, find those intercepts for me. So guys, I know I did mine quickly, 1, 2, 3, 4, 5, 6, 7, it looks like I had mine -7, you can't count, you gotta actually find them. And it looks like it is headed toward the y-axis of green, so it's going to intersect the y-axis. So I need to find precisely where are these intercepts. And I'll come back, refine that green graph, and leave it. Anyone tell me, how can I find precisely, and not just guess, where is that x-intercept going to be located? Yes, sir?
You're gonna replace the y or the x values with 0.
Replace the y with 0. So to find an x-intercept, you always substitute y with 0. Okay, we're going to, where's this? That's where you find an x-intercept. You always have y equals 0. If you're on the x-axis, the y is 0. But the order path makes sense. Now you gotta solve this. I can solve this easily. Move the 4 over. You can solve it easily. Just move the 4 over. You can multiply or divide both sides by a negative and get rid of those negatives in this case, which is nice. You have that. And I'm sure at this point you would say, Professor, if you actually solve it, now square both sides. And you're going to end up with 16 is equal to x plus 9. Subtract 9, I think you get into the 7. And we'll write this as ordered pair, 7, 0. That's my x-intercept. Now, I did a rough sketch. I don't know how close to that I was originally. I just did a rough sketch on that green graph. So we'll go back now. I know precisely now it's 7, 0. Yes?
What about the negative in front of the radical?
Right here?
Yeah.
I multiply both sides by a negative to get rid of it.
I see.
Or divide both sides by a negative. I'm sure. Here's both of them out. Good question. That's true, guys? Now, precisely the y, that was the x-intercept. The y-intercept. We said, yeah, Professor, it's headed here this way. You haven't drawn it over there yet. But it's going to cross the y-axis. The green. Looks like you're going to cross it in the on the negative side of the y-axis. Guys, can anyone tell me precisely what would you do to find precisely where is it? Find the y-intercept on any graph. This one I replace y by 0. Yes?
Replace x by 0.
I have to replace what by 0?
X.
The x.
X.
So if I go to my function, he's telling me, Professor, replace that x by 0. If you want the y-intercept. That's just a little technique. This is easy. This one will be easier. That's square root 9 plus 4. I think it will end up with a -3 plus 4. And my math is correct, it's 1. I've got 0, 1. I've written this word there. Now I know precisely where my x-intercept is, my y-intercept is, so I can go back and modify my green graph a little bit, make it a little bit better. 1, 2, 3, 4, 5, 6. Wait, 1, 2, 3, 4, 5, 6.
How did it go to 1 line?
I do have, is that -7? I'm just counting. I'm not doing it on the counting. Don't get excited. Was it 7 or -7?
7.
Oh, beautiful. So what happened here? Looks like it's going to intersect the x-axis over here, does it?
No.
So what happened in this little process? And she had a question earlier. Did we set this up correctly, guys? I set the y equal to 0. I tried to solve it. Yes or no? Or did Ramsey set you up to make you think a little bit? Vert-
that steep.
Looks like, please tell me, that was the parent graph looks like this, or square root. Then we did this to it, we reflected it across the x-axis. It looks like that. And then I think we're supposed to what, vertically shift it up what? 4. Is it true? What do we do? What did I do here? It set you up. I set you up. You're just sitting there and I see his head nodding. Oh yeah, Professor, anything you say, Professor? I set you up. And I was not gonna tell you until now, you know. If I finish this up, I had an x-intercept, if there's no mistake, what, 7, 0? 7 zeros over here. My green graph is intersected over here. So there's something wrong. Caught you. Now, can anyone tell you where the caught was? Did we do all the transformations correctly or not?
You can put the, point back.
Okay, you make it, go back, okay. Jonathan says, wait, Professor, that green graph, go back, -9 up 4, you said, right there, which I think we had earlier. True? Now, here's the reason I asked you for the x and y intercepts. If you say, oh, Professor, I'll just go quickly, like you did, and my graph, which I did quickly, looked like that. Is that true? Then when we slow down and actually find where should it cross the x-axis, we missed it. Let me go ahead and put those x and y intercepts in there. I hope they're correct. Guys, we think the x-intercept is what, 7, 0? So that means it's over here on the other side. Set you up here. We think it's there, and the y-intercept, we think, if there's no mistake, this is the x. We think it's 1 for the y-intercept. Let me make this a little larger. Is that true? X-intercept, y-intercept, endpoint. Do we now have those? Now, when I connect, I'll have papers turned in, all of a sudden the student gets their paper back, oh, Professor got a 0 on the quiz? Well, you had the wrong graph. I did what you said to do, I went did right here, and I went, like that. You know, you have to find the x and y intercept, so when you do that, more precisely, and guys, this thing is very steep, it's gonna have a curve, something like this. It's gonna come down and pick up that. That's the y-intercept at 1. It's gonna come on down, travel over here of all things. As it travels over, it's gonna pick this up. Now what's it gonna do? Is it gonna cross over? Yeah, it's supposed to cross over the x-axis, and where it goes from there, it goes, it's underneath there, guys, now. And start here, and continues forever, and it should be underneath there. It's crossed over. Wow. Do we agree with the graph now? Why, of course. The first one looks so cute, though. I just did it real quickly. You guys said that, oh yeah, Professor, that looks good. All the transformations. And pay attention to precisely where are the x and y intercepts. Now, before I close this down, anyone tell me on that green graph, what's the extent of the domain? And you gotta keep in mind, this is the endpoint. From left to right, what you say along the x-axis, what's my domain? On that green graph. Oh, axis. Is it out to a -9 for the furthest to the left is a -9 bracket. Now how far out implied does that green graph go? Forever. That's my domain. Range, be up and down. Based on the sketch, guys, the up and down, is it implied here this is going to cross over, of course. As it goes this way, is it also dropping down? So from here to here, you would describe the range as Negative infinity up to where was this endpoint again? 4. So negative 9 up 4. So negative infinity up to 4.
Right.
What's that? Oh, you mean the interval? Why did I put negative infinity first? Right. Yeah, because this thing is going to, where was that range? It's going to drop down, it's down here, and goes up. Up to 4. So the negative infinity says it is below, out here, it's below. So it's dropping down forever. And it's going to go up to 4. Not a big question, I see.
If you were to put, bracket 4, comma, negative infinity. would
No,
that
no,
be
no, no,
zero?
no, oh, good question, Jonathan, no, you put the infinity first.
That's negative?
Negative. So it's negative infinity up to 4. Go right backwards. Negative infinity comes first. It goes up to 4, least to most. Good question, though. Guys, that help? I had to do that before I leave chapter 1. Now, I'm watching my time here. Does that make sense, though, the way we approach this? Took a little bit more time than what I thought, but I think it's quite honest. How to do transformations. Guys, any questions? I think I've done enough on that. Okay? I'm gonna erase this, guys. Now, I think we're closing down chapter 1 now. Now, I'm anxious to get in chapter 2. But, before I do it, if I did do it. Well, I did. On that same handout. Flip it over, guys. Is this the one that has the word problem? Did I also tell you which page number in your textbook and which particular problem I just brought out of your textbook to look at? That's the way they close out chapter 1. Now, I'm not gonna have time today to look at all 10, how many did I get, 4? I think of 4. I'm gonna look at some of those with you today, but there are a couple, and then pick up the other couple later on, because I wanna move into chapter 2. I thought this was a beautiful presentation on transformations. What to do, when, and I love these. We'll definitely have to practice more of these in your homework, where they give you just a point, and ask you where is that point going to land. And all those transformations. This, of course, also is to apply the transformations. Okay. Now, here's what I want to do. I want to need a student to help me. I'm thinking. Would someone read number 3 first? I may not, if I recall what number 3 says, I may hold off on that. But let me have a student first start reading. Let's see if this is the one I'm thinking about. Go for it.
So an open box with a square base is required to have a volume of 10 cubic feet. Express the amount of material used to make such a box as a function of the length x of the side of the square base.
So that's number 3. Go back to number 1.
An open box with a square with, an open box with a square base is to be made from a square piece of cardboard, 24 inches on a side, by cutting out a square from each corner and turning it up the sides.
Those 2 are about boxes. Would you read number 2?
Water is poured into a container in the shape of a right circular cone with a radius 4 feet and height 16 feet. Express the volume of water in the cone as a function of the height h of the water.
Number 2 is the toughest one. I know there's another one, number 4 down there. That number 4 is gonna be easy when we finally get to it. So I want to take a look at the 2 box problems with you, okay? And the time I have left in chapter 1 will be finished for the most part. Bill, do me a favor. You read those, I'm gonna ask you to read again. I'm gonna stop you at various places. Hang on here. We're gonna do these 2 box problems. Can you imagine the next exam? Okay, hang on. part one, applications. We're gonna have some students in class who come out, or will probably become engineers. They need some applications of this math, or some other field where you need the applications. Phil, could you read that number one to me one more time, and you try to translate and get that worked out?
So an open box with a square base is to be made from a square piece of cardboard, 24 inches on the side, by cutting out a square from each corner and cutting up the sides.
Now, hold on, and that's all they're telling you right there. Fine. Got confused. Yes. He says a square piece of cardboard. Well, it's not square, I'll visualize what's going on. We're gonna take this. Yes. He says, Professor, they want you to go to each corner and cut out, I think from what I heard you read, a little square. From each corner. It's a rough demonstration. We'll see what happens. Every corner. By the way, these little squares I'm tearing out should be the same size. Make it fit the problem. Now, as I tear this out, little squares, that's what Phil's going to do. I think next I heard you say something about fold up the sides. Well, I fold up the sides with what I've just done, and I'll be careful you guys and show what that might look like. Rough sketch here. I'll give you a visual here of what we're asking you to do. Now please tell me, is it possible to form a box? An open box, I'm gonna be open. Is it, if I go through what he asked me to do, go to each corner, cut out a little square, fold up the sides, is it possible to form what they consider a box? Now, but they were telling me something about this box. Now, hang on. Bill? Remind me, that square piece of cardboard, I think it was, had dimensions of something. So help me out. When I finally get this sketch, and tell me what size cardboard was I looking at?
So it's to be made from a square piece of cardboard that's 24 inches on the side.
Hang on, it's 24 by 24. And of course, the units, inches. Square piece. You saw what I did roughly? He's saying, Professor, don't stop there. Show that you're supposed to go to each corner and cut out a square. Supposed to be the same size. Ruin this. What's the size of those squares? Did they tell you what size squares? Is it a 3 by 3 for the squares? 1 by 1, 2 by 2 to cut out? Did they say?
Just cutting out a square.
Yeah, a square, I don't know, so we'll call the sides of these little squares x by x. I have no idea what size am I cutting out. So saying after you do that, and I gave you the visual there, after you do it, you're supposed to be able to form a box. Did they describe the box for me, Bill?
It just says, so by cutting a square from each corner and turning up the sides. And then it says express the volume of the box as a function of the length x of the side of the square cut out from each corner.
Okay, so I should be able to form a box like I did on my visual there, my demonstration. You're saying I'm supposed to do this. Make somewhat of a box here and we'll get this problem done. like that. Not bad. Not bad. That's what we're asking. And what else? Read that to me one more time.
So last thing it says, express the volume of the box as a function of the length x of the side of the square that's cut out from each corner.
So they want to know the volume of this box. How much water would it hold if I poured water into it? Volume. Guys, does anyone in this class recognize what, how to find the volume, cubic units, a box would hold? I think it's like a standard formula. Yes?
I think it was, I don't know, if it was side multiplied by side?
No, severe, you're thinking about something else. Yes?
Length times width times height.
Yes, to find the volume of a box, you need its length times its width times its height. Now, he tells me this box came from this. So you guys gotta do a little thinking here. The original length, was 24. Has that been cut short? You saw me tearing out little corners. Has that been cut short by the time I get to the length of the box itself? How much short has it been cut?
So it's
An X here, and an X here. 2X. So we'll represent this as 24, subtract 2X. The width, right here, of my box, came from, I think, this. That's true, guys? Has that also been cut short? It was originally 24 by 24. It's been cut short what? An X up here, an X down here by the time I get to the box. So it's 24 subtract 2X. Now you saw me do the visual. Oh, rough demonstration. I need the height. Does anyone think they know, even from this rough demonstration, what on earth will I represent the height as? And in my case, it's that little piece right there in the corner. Miriam, go for it. That's X itself. And I fold the corners up, guys, this little corner this right here, as I flip it up, as I did my demonstration, that's gonna act as that height. If Miriam told me, you guys agree? So all I need to do is multiply those three together, length times width times height. Aiden, I think you get the formula to me. So here it goes. And by the way, guys, if I multiply all three of those together, are all three length, width, height in terms of X? So let's write this as a function. Not f of X in this case, but V for volume. V of X. It's all in terms of X. Length, 24 subtract 2X. Width, 24 subtract 2X. Height, X. Better expressed as V of X, volume with respect to X. I like that X out front. Let's rewrite this as 24 subtract 2X squared. I would not ask you to expand that out. So there's the volume expression for this. Length times width times height. You can't go wrong with this. Makes sense, guys? Length times width times height, the way we label everything. Now, I wrote it as a function. If I write it as a function, Samir, usually if I write something as f of x, g of x, and v of x, usually I'll ask also for this before you leave it. What is the domain of that function? Functions have domains. Mine looks like this. This is my function. Are there some restrictions on the x? I'll tell you right now, x can't be 0. That would give you a volume of 0. I don't think x can be a negative number, because volume can't be negative. Is that true, guys? So there's some restrictions. I'd like to know, what is my domain? Does anyone in this paper class have an idea of how to come up with, I don't have a graph here, so I can't look at the graph and say go from left to right and find the domain like I did maybe over there. Guys, it's based on this right here. What am I allowed to replace x by? And be whatever. It has a domain. Is it all real numbers? No.
0 to 12.
Like them again. Or someone say something. Samir? Well, I need, let's put an interval notation. You see a 12 in there somewhere, so do I. I think. Come up with a clever way to find the domain? Yes.
If I'm not mistaken, it's -1, 2 plus infinity.
Well, if you think -1 through infinity,
Yeah.
hang on.
Open. It should be open. Open -1.
Oh, open, you want the
Open,
negative
yes.
one open,
No, open. Open -1.
right here. Want this like that?
Yes.
Guys, can I replace x by a negative number to begin with? To get volume, volume is always positive, it's a positive number. I can use negative numbers. Don't help me out. I don't want volume to be 0. Hear him.
I believe it is open parentheses 0 to 12, also open parentheses.
Oh, you're saying I can only use those numbers. Miriam, let me go outside the domain. 13. You're saying I can't let x be 13?
Correct.
What would happen if I put a 13 in there?
You'd have a negative length.
Okay, if I go back here, guys, you look back at the box, the original box here. Just wait, Professor. If that's a length way back at the original box, you know that's gonna be positive for a length. And she, I think in her mind, she said, wait, Professor, I'll solve that for you right quickly. Reverse my symbol here. You got that? Is that true? Now I think it's gonna happen also here, on this one. And think that the height is merely what makes sense here? It's gonna be positive. So she put those together, she says, Professor, there it is in interval notation. It's greater than 0, less than 12. Written in interval notation. You get outside the domain, it's not gonna make sense. So 0 up to 12. Does that make sense there? Okay. Beautiful. Oh, this is taking me right to where I wanna go. We'll stop here, guys. Okay on this? Now, Philip, since you're close by, would you go down and read number 3 for us, and we'll take a break.
So, number 3 is an open box with a square base. Is required to have a volume of 10 cubic feet, and then express the amount of material used to make such a box as a function of the index of a side of the square base.
Beautiful, beautiful. Read that to me one more time, and I'll stop you at various places to close this down.
So, an open box with a square base is required to have a volume of 10 cubic feet.
Stop right there. Guys, bear with me, this last box one, sketch. He's telling me it's, I think you described it as open box. And it's supposed to be something like this again. Quick sketch here. I'm making this one a little crooked. Okay. And Philip, I'm having you pick up here shortly. On this box. I want to take a break here. Chapter 1 right now will be finished. Okay, guys, we'll use that. Now read that to me one more time.
Yeah, so, an open box with a square base is required to have a volume of 10 cubic feet.
Stop right there. An open box. Guys, what do they mean by open box? What's the difference between an open box and a closed box? Yeah, the open boxes, they use the word open, what, there's no top there, top is open. So that's one part I need not worry about, the top is open. And then you're telling me it has a square base, I think.
Yeah.
Is that true?
Yep.
Okay, now, did they tell me the dimensions of the base?
No.
2 by 2, 4 by 4, no, someplace X and X. Did they tell me the height of the box? No. Can I call the height also X?
You can say it's X squared.
No, because what would happen if I let the height be also X, I'd have what? Dimensions to be X by X by X. That would turn that into a cube. They didn't mention the word cube, did they? No. So the height is something, but he's saying, Professor, they didn't tell me what it was. Use H, height. Now you're saying the volume of this box, and guys, I think we did something with volume over here. Is it length times width times height? Okay. So the volume was, Philip, tell me, was it 10?
Yep.
Cubic something. Okay. Now if I use my formula length times width times height right now for the volume. Length times width times height. Volume formula, would I end up with this? Is that the expression for the volume at this time? X times H. And that's equal to 10. And you would get partial credit. Phil, what do they ask you to find?
They're asking you to find the, so you need to find the amount of materials used to make such a box as a function of the length X and the side of the square base.
Oh, so they gave you the volume. Over here, they asked you to find the volume. On this one says, no, I'll give the volume to you, it's 10. So hold 10 cubic units of water. They're saying, how much material does it take to construct that? You're going to make a trip to Home Depot and buy some lumber or something. You're going to make a box. Now, how much should I buy? How much is it going to take? Guys, it's called area. So I need the area of that box. Now, when you think about area, you say, Professor, I know how to find the area of the rectangle. I know how to find the area of a circle. I know how to find the area of this and that, and so forth. But here, it's unusual to say you need the area of that box. They call it surface area. Now we just use A for area, surface area. Guys, I need the area of that box. And I like to have it in terms of X. Like f of X, still doing functions. Okay, now keep in mind it's open at the top. Now, does anyone have a suggestion to close down before we take a break? How can I express the area of this box? And I'll give you a hint that has 5 parts to it. The top is open. You're not worried about the top. What might you do with those 5 parts that we have on this box? Go for it.
5X squared.
No. I knew you were going to say that. That's why I said no so quickly. I knew. Far by.
So we rule out the H, like,
Oh, we're not gonna rule out the H yet. Tell me first, you set me up. How are you gonna find the area of this box? And this box contains 5 pieces.
area.
5x squared.
And are all, by the way, are all 5 pieces rectangular or squares?
Just
No circles involved, I hope.
5xh.
Oh, get close. Get close. That's why I love this problem. Jonathan.
4xh plus x squared. I think
Oh, get close. Oh, wait, you may have had it.
it's
Hang on, hang on. Let's see. Okay, before we take a break here, I understand what students are saying. Guys, what I would do, if we want to express the area of this box, I would tear it apart. All the pieces are rectangles. And you can walk across the street to that middle school, they know how to find the area of the rectangle. They'll say base times height, or length times width. So I would tear it apart and say, wait now, if you want the area, surface area they call it, of the box, Professor, tear it apart. Find the area of each piece that makes this box. Well, I'm gonna start with the base. Area there, what's called A, length times width is x times x is x squared. That's done.
Function
Now, I would like to just jump up to the top and shade that also in red, and say also express the area of the top, which I think would be another x squared. But Phillips tells me the top is open. I don't have to worry about it. Okay, got the base out of the way. Are there some other pieces to this box that maybe I'm overlooking? Of course there are. On the markers here. Here's another rectangle. On the side here. That's true, guys? If you visualize that green rectangle pulled out, I need its dimensions, length and width, for that rectangle. Guys, is the height here and the x here on that side rectangle? So if I multiply these two together, this length times width, I hope, is that xh? Okay, so that's in the greens, xh. Now, I'm gonna travel directly across and shade in green this one. Please tell me, is that one that's directly across another xh? Now there's three of the, I said five, I guess. Three of the five pieces. Well, where's the other pieces? Well, there's a piece stuck out front here on the box. Anyone look at this and visualize for me the piece stuck out front of the box? I'm not going to shade it in. What would its area be? Is it an XH? The one stuck out front?
Yeah.
Okay, that piece there is an XH. You put that in black. And the one in the back here, which I did not shade, is that another length times width x times h. Is that true, guys? Jonathan, I heard what you said. You said, Professor, the area would be, at this point, write this in black, would be x squared plus combined like terms 4xh. You guys agree? Whew. Who was reading for me? Well, since you don't, go down to the end so we can take a break here shortly. Go down to the end and see what were they asking me to be. Be specific.
So the one you just expressed the amount of materials used to make such a base is a function from the length x.
Oh, wait. Function of x. So they're saying your final answer must be function of x. F of x. G of x. In my case, A of x. Here's my answer. So what's the issue? Am I finished? Just turn my paper in? Or have I read the directions carefully? Or did I just turn my paper in and say, hey, Professor, that's the answer, x squared plus 4xh. No, what they say to do? Have your final answer in terms of only what? X. That means to close this down, this is gotta go. I can't leave h in there. They want everything in terms of x. Now, I think I heard a student tell me way back, far about, I think it was you. I got this earlier. Anyone be clever and tell me, I need a replacement for h. And when I put that replacement in, I'll fit everything in terms of x like they wish. Can anyone tell me what might I do?
Place of one.
No, what can I do right here? Easily done.
10 over x
And
cubed.
over
Can I solve for h? Can I divide by x squared in that relationship we had earlier and put a comma here? These will cancel. H will be equal to, when I solve for h is equal to that. I now have a substitute. Welcome to pre-calculus. I have a substitute for h. And when I put that substitute in, it's now going to look like this. X squared plus 4x, and here goes. In place of h, the substitute is 10 over x squared. please tell me at this point, is everything in terms of X now? I'm gonna write my final response, guys, like this. X squared plus, here goes. If I clean this up, I see 4 times 10 is 40. And I could cancel one of these X's out, in algebra, and end up with 1X in my denominator, X in the X squared. I'm gonna leave the answer like that. As a, expression for the, area of the box. Did they ask me to do anything else with it?
I think that's all, of the length x over the side of the square base, I think it's.
That's the way it ended. Well, we ended it, yeah. They didn't ask me to do anything else with it, did they? Oh. So you guys would make me think about engineering? Something might involve, and all of a sudden your boss gives you a problem to work on. You know how those bosses are. I have some friends who are engineers. They just go to their offices and they're getting what they want, and you've gotta construct this and construct that and go crazy, and all of a sudden you've got this box the wrong size, you lose your job. You lose your job. Or the bridge collapses. You really would lose your job. Okay? So guys, any concerns about these first two here on the handout? Now, after the break, we'll instruct you on two. Which I think will be a breeze for us. So you guys, 15 minutes, 5, 10, 15, just so we